नमस्कार बच्चों। आज हम लोग ग्रेड 11 केमिस्ट्री सेकेंड लेसन एटॉमिक स्ट्रक्चर का कुछ पास्ट पेपर क्वेश्चंस देखने वाले हैं। सम JEE एंड नीट पास्ट पेपर क्वेश्चंस। ओके, so as we are doing, please take the screenshot of the questions. Okay, so let's get started. So this is the first question. If you can see, the ratio of the wavelengths of the light absorbed by hydrogen atom when it undergoes transition from N2 to N3 and N4 to N6 is, so you have to find the ratio when they undergo the transition. Okay, so let's get started. So I'll just share the whiteboard. The wavelength is given by Rydberg constant Z square by 1 by N1 square minus 1 by N2 square. Right, this formula we have studied. So first one is the transition when from 2 to 3, n is equal to 2 to n is equal to 3. So we write like this, and it is for hydrogen. So Z is equal to 1 because it is for hydrogen. So 1 by 2 square is 4 minus 1 by 3 square is 9. So we get 36. This is 1 by lambda 2. Now if I want to find out lambda, we get 36 by 5R. Okay, so this is the value of lambda when it is transitioning from second to the third. Now there's yet another value we have to find out so that we can write in the form of ratio. When lambda is transitioning, when the electron is transitioning from 4 to 6, we use the same formula. R Z is 1, 16 minus 1 by 6 square is 36. So we have R. So students, in order to make the calculation simpler, I'm taking 1 by 4 common. Okay, so when I take 1 by 4 common, it is 1 by 4 minus 1 by 6. Sorry, 1 by 9. Okay, so this will make so R by 4 this is 5. Okay, so this is 1 by lambda. So I want to find lambda, so it will give me 36 times 4 by 5. Okay, so they have asked for the ratio. So this is equation 1 and this is equation 2. So what I do is I take the ratio for this equation 2 to 3 by lambda 4 to 6. So 36 by 5R by 36 times 4 by 5R. So when I cancel the common terms, I get 1 by 4. This is your required ratio. Okay, so So this is your required ratio. So students, if you see, you have the required ratio 1/4, so B is your answer. Okay, so B is your answer. B is your answer. Now, please read the second question carefully. So, the second question, radius and energy of the first 4 orbit for helium ion and lithium ion. Okay, and one given, that is for hydrogen. Okay, so let's get started. Second question, for energy, whenever the energy you need to find in joules, okay, we use this formula, minus 2.18 times 10 raised to minus 18 z squared by n squared. This is for joules. Okay, if it is an E in EV, we use the formula minus 13.6 z squared by n squared EV. Okay, so that we have learned. Okay, now the expression for radius of the nth shell is equal to 52.9 times n square by z square pm. Okay. Now, in case of energy for the helium ion, for helium ion, Z is equal to 2. Okay, and this is the first orbit, so n is equal to 1. So this is for helium ion. So we get minus 2.18 times 10 raised to minus 18 times 2 times 2 is 4 by 1. So this comes to minus 8.72 times 10 raised to minus 18 joules. Okay. Now, similarly for lithium ion, Z is equal to 3. So minus 2.18 times 10 raised to minus 18 times 3 square is 9 by 1. Orbit is the same one. So this comes to minus 19.62 times 10 raised to minus 18 joules. Okay, so these values you are getting. And for radius of helium ion, you're getting 52.9 times 1 square is 1 by Z is 2. For helium it is 2, which comes to 26.45 pm. Okay, and radius for lithium is 52.9 times 1 by 3. This comes to 17.63 pm. Okay, so this formula you will use when it is in pm. Okay, and when it is in Armstrong, you have to use the value of 0.5953. Okay, so these are the values. Okay, so they gave this as a multiple choice question, and these were the values you got. Okay. because they have given you the values over here. As you see, they have given the energies of the hydrogen and the radius in PM and joule. So you had to use the joule value and the PM value for finding out the energy and radius. Okay. Now coming to the third question, the quantum numbers of the first 4 electrons are given below. You have to tell the correct decreasing order of the energy of these electrons. Okay, so we use N plus L rule. Okay, so for the first one, we have N is equal to 4, L is equal to 2. So this is 4, D, you know the L values, then L is equal to 0, 1, 2, 3, 0 is S, P, D, F. Yes, so we have done this. In the second one, it is N is equal to 3 and L is equal to 2, that is 3D. Now, third one, we have N is equal to 4 and L is equal to 1. So that is 4D. In the fourth one, we have N is equal to 3, L is equal to 1. So that is 3P. Now, we also know that the higher the value of N, more is the energy. So, definitely, the first one will have the highest energy, right? Then the second one, here students, if we apply the N plus L rule, this is 6, this comes to be 6, this comes to be 5. We follow the N plus L rule for the energy, right? So this also comes to be 5 and this comes to be 4. Okay, so 1 is greater than 2, which is equal to 3, which is greater than 4. But among 2 and 3, if you see, you have to determine in terms of principal quantum number 3 and 4. So, principal quantum number 4 will have higher energy than 3. So, 1 is greater than 3, is greater than 2, is greater than 4. So, this is your answer. So, B is your answer. Okay, so this is how you do. So, first you determine N plus L, and then if you have some equal, if something is coming as equal, you check with the principal quantum number. Okay, so this is your answer. Okay, students, I'll share the next set of questions. Please take a screenshot. So all these 3 questions we did. So if you see, B is the answer. Okay. Please take this screenshot of the question 4 and 5. So the energy of an electron in the ground state of helium is minus x joules. So this also in joules. Then for an electron in N2 states of beryllium, 3 plus ion is, okay. And please take the screenshot of the next question as well. Okay. Okay. Question number 4. We have energy in joules is given by minus 2.18 times z squared by n squared, right? So for helium, z is equal to 2. So minus 2.18 times 4 by first orbit, so 1 square, 1 square. So this comes to minus 8.72 times 10 raised to minus 18 joules. Okay, and they said this value is represented by X. Okay, so this is for hydrogen. So this is for helium. Okay, now this is for the ground state when n is equal to 1. Okay, now for beryllium ion, okay, where for beryllium Z is equal to 4. Okay, this is helium ion, beryllium ion. So beryllium is, they have given as 3 plus I. Okay, now this beryllium with Z is equal to 4, so that means electrons will be 4. But out of the 4 electrons, because it is beryllium 3 plus, so how many electrons it has lost? 3 electrons. So it is left with 1 electron. In this case, if you see helium, the atomic number is 2. Helium, the atomic number is helium, or atomic number is 2. So that means electrons are 2. So, but they have written helium plus. If it is helium plus, so that means this, out of the 2 electron, 1 electron is lost and it is left with 1 electron. So if you see, both of them behave as hydrogen. Okay, so hydrogen, helium plus, lithium 2 plus, beryllium 3 plus, they are all called as hydrogen-like atom and they follow the same energy rule. So beryllium 3 plus will also follow the same energy rule. So it will have the energy of minus 8.72 times 10 raised to minus 18 joules. That is equal to X. So X is your answer. Okay. So students, please remember the hydrogen-like species behave in the same way. Okay. So hydrogen-like species behave in the same way. So this is your answer. Okay. Now students, coming to the next question, where they have asked about the different quantum numbers and what do they signify. Each quantum number, what does they tell you about? So we discussed in the video also, what does they tell you. Okay, so the principal quantum number n tells you about the energy. It tells you about the energy of orbital. And azimuthal quantum number tells you about the shape of the orbital. The The magnetic quantum number tells you about the orientation of the orbital, and spin quantum number tells you about the spin of electrons, minus E or plus. So let's check where this option comes to. Okay, so here your option comes to B. Okay, so your answer is B. This is your answer. So see, you have to know what each quantum number denotes. Okay, so they might ask as a multiple choice question. Okay, so coming to the next one. If A0 is denoted as the Bohr radius of hydrogen atom, okay, then what is the de Broglie wavelength of electron present in the second orbit of hydrogen atom? Okay, so you have, please take a screenshot. Okay, so A0 is denoted as the Bohr radius of hydrogen atom. And what is the de Broglie wavelength of electron present in the second orbit of hydrogen atom? Okay, so coming to the sixth one, R0 represents the radius is represented by A0. Okay, and we also know the radius is given by A0 n square by Z. Okay, the radius is students, in the question itself, we have studied the expression of radius as like this: 0.529 times n square by Z Armstrong. So this is what we studied, right? So here, because they have given the value of radius as A0, they have given for value n is equal to 1, first orbit. Okay, and they said Rn is equal to 0.529 Armstrong. Okay, and they have also given in the question itself radius is equal to A0. So that means A0 is equal to 0.529 Armstrong. Now, here we also know from the question, when n is equal to 2, R is equal to what? 0.529 times 2 square by 1. Okay, so R is equal to what? 4A0. Okay, so here, from Bohr's hypothesis, from Bohr hypothesis, we also know that the angular momentum of an electron is a whole number multiple of nh by 2 pi. We learned this, right? So over here, if I am rearranging this equation, 2 pi r is equal to n, 2 pi r is equal to nh by mv. So I'm just rearranging the equation. 2 pi is equal to nh by mv. Okay. We also know the expression for lambda is given by h by mv. We have this in our hand. So we can substitute this value. 2 pi r is equal to n lambda h by mv. We can substitute it with lambda. So we get this expression. Okay, so 2 pi r is equal to n lambda. Now, in this equation, so we have this equation, we have this equation, and we have this equation. Okay, now if we substitute the value of r, so I put this as equation 1, I put this as equation 2. Okay. Now over here, if I am substituting the value of equation 1 in equation 2, so 2 pi, instead of r, what can I put? 4a is equal to n lambda. So what is the value of lambda? 8 pi a naught, because here it's an a naught by n, where a naught is nothing but the radius of the hydrogen atom. So this is the expression for the wavelength that they have asked. Okay, so students, what we did, we wrote the expression for the radius. Okay, and in the question itself, they said that this value is given to you as a0, so we take it as a0 itself. Okay, so we don't use 529 because 0.529, because a0 is already given to you. The same thing we apply for our second orbit. Okay, so same thing we apply for the second orbit of hydrogen. This is for the second orbit of hydrogen, and we find out the radius. And they have asked the wavelength for the second orbit of hydrogen. So for the second orbit, according to the according to the Bohr hypothesis, angular momentum is an integral multiple of h by 2 pi, nh by 2 pi. And we also know the expression for wavelength given by de Broglie, that lambda is equal to h by mv. Okay, and we substitute these in the equation, and then we get the required wavelength. Okay, so basically you have to find out the de Broglie wavelength. Okay. Now students, question number 7. I hope you have taken the screenshot. Question number 7, there is a set of graph given for the E versus Z. Okay, so E versus Z. So E versus Z. So for hydrogen-like species, which of the following graph provides the most appropriate representation of E versus Z? E is the energy and Z is the atomic number, and N is the principal quantum number. Okay, now please take a screenshot. Okay, now coming to the question. So E versus Z. Okay, now students, you know the value of energy in the nth orbit, minus 13.6 Z squared by N square. Okay, so EV, even if you are using the Joule one, no problem, because we are concerned with Z and N. Okay, so we get minus 13 point, or rather I'll keep the minus outside, minus 13.6 by N square Z square. Okay, so energy. So they are plotting energy and Z. Okay, the energy and Z. Okay, so looking at this expression, and N is a constant. Now, looking at this expression, it's like energy is directly proportional to Z. Okay, and it comes like this, as an equation comes like this, minus mx square. Okay, so graph is like that of a parabola, where y is represented by E and x is represented by Z. Now this equation is that of a parabola. Okay, so parabola moving in the, so for parabola there are two expressions. For parabola there are two expressions. First one and fourth one. First one and fourth one. First one where the parabola is a positive slope. This is the first one, and the second one, the parabola has a negative slope. Sorry, the fourth one, fourth option. Now, in this equation, if you see, the slope is negative. So that definitely the answer will be the fourth. Okay, so this is the answer. The fourth one is the answer. Right. Now, students, the next question, hope you have taken the screenshot. The spin-only magnetic moment of chromium ion is, okay. Now, students, here, chromium, first of all, let me tell you the formula of magnetic moment. Mu is given by root of n plus 2. Please remember this formula, okay? Sometimes they ask a direct question like this. This is where n is the number of unpaired electrons in an orbital. Okay, now next, coming to chromium. Chromium has an atomic number of 24. It will be given in the question paper. Don't worry about it. So we know the filling up of electrons, right? How the electrons are filled. So we have the Aufbau principle here: 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f. Okay, now first, this as I'm doing, I'm revising also. So 1s2, 2s2, 2p6, 3s2, 3s2, 3p6, 4s2. Now how much it came? 6, 6, 12, 24. Now students, this many atoms are 18, sorry, this many electrons are 18 electrons, which is the atomic number of argon, the noble gas argon. So most of the time we represent like this: argon. In most of the books also you would have seen. So argon 18, 4s2. So this is an expression we use for different if the number of electrons correspond to the noble gases, we represent like this. So this particular 18 electrons correspond to 18. So argon. So we represent like this. Okay. So this is the configuration for chromium. Okay. Now students, what they have asked is not chromium, but for chromium 2+ ion. Okay. So chromium 3+ ion. Now, chromium 2+ ion, that means how many electrons are lost? 2 electrons are lost by chromium atom. So here, from where they will lose the electrons. Usually, when they have to lose the electrons between S and D orbital, usually they lose from S orbital. So because it's easier to lose, okay, from there. So how many electrons it will lose? The 2 electrons. So AR18, 4s0 because it loses both of them, and 3d4. Okay, so that means 4s is empty. In 4, how many? In 3d, how many electrons are there? 4. All the 4 of them are in the R. First, we follow the Hund's rule that once they are first unpaired, right? Filling will come only later when they have more electrons. Okay, so it is unpaired. So how many unpaired electrons are there? N is equal to 4. Not paired, right? So mu is equal to root of 4, 4 plus 2, which comes to root of 24, which is 4.90 dm. Okay, so this was given as a multiple choice question. Okay, so please remember this formula. And about how they lose electron, we have a lot of questions based on this, so it will be more clear. Now students, coming to the next question, In a multi-electron atom, which of the following orbitals described by 3 quantum numbers will have the same energy in the absence of electrical and magnetic field? Okay, please take a screenshot. Okay, so choose the correct answer. So the first one, if you see, it is 1s. Okay, so let's try doing it. Okay, here in order to check the energies, we always use the n plus n rule. So n plus L rule, right? The first one is from the values given, L value is 0, 1, 2, 3. This is S, P, D, F. So first one is 1s because n value is 1 and L value is 0. So it is 1s. Second one is n value is 2, L value is 0. So it is 2s. Third one is n value is 2, L value is 1. So this is 2p. Next one, n value is 3, L value is 2. That is 3d. Next one, n value is 3, and L value is again 2. That is also 3d. Okay, if we have n plus L rule, we see that D and E have the same value of n plus L rule value, right? That is equal to 5. 3 plus 2, 5. So both of them are having the same energy. Both of them will have the same energy. And we know that all the d orbitals have the same energy. Okay, and all the p orbitals will have the same energy. Okay, so clearly D and E as our answer. Okay. Students, come to the 10th question. Okay, so in the 10th question, heat treatment of a muscular pain involves radiation of wavelength. They have given the wavelength in nanometers. Okay, which spectral line of hydrogen atom is suitable for this line? Okay, so you have to choose the series. Okay, so they have given you the value of Rydberg constant. Okay, and h and the speed of light. Okay, now sharing the screen. Okay, so the values that they have given is, we are doing the 10th one. Okay, so they have given you the value of Rydberg constant. So 10 raised to 5 per centimeter. And the wavelength given is in nanometers. Okay, 900 nanometer. Okay, so we have to make it into meters. So that makes to 900 times 10 raised to minus 7 meters. Okay, and (900 times 10 raised to minus 7 centimeter). Okay, so basically nanometer to centimeter, you have to just multiply with 10 raised to minus 7. Okay, now you know the value of the wavelength, I mean the formula for the wavelength. Now this is Rydberg constant, z square by n1 square minus n2 square, where z is equal to 1 because it is for hydrogen atom. Okay, now coming to 1 by lambda RH, this is 1 square. Okay, so 1 by n1 square minus 1 by n2 square. This is what we have to know, because when we know the value of n1 and n2, then only we will know which series it is. If you see the options, you have to look for these n1 and n2 values, or rather, when you know the n1 and n2 values, we will know from which energy orbital the jumping of electron has taken place. Okay. Now, we know the value of lambda and we know the value of Rydberg constant. So 900 times 10 raised to minus 7 times 10 raised to 5 equal to 1 by n1 square minus 1 by n2 square. Okay, now, here there's a little bit of trial and error method. Okay, so here this gives, if we solve this, it gives, this gets cancelled. Here we get minus 2, right? So this gets cancelled. This also gets cancelled. So I get 1 by 9. Okay, now, so now a trial and error method we have to use. 1 by 9 is equal to 1 by n1 square minus 1 by n2 square. So what transition or which of these values, if we substitute, we will get 1 by 9. Suppose if I take n1 is equal to 3 and n2 is equal to infinity. Okay, you will get an idea from the options itself. Okay, so if I get, so 1 by n1 square is 9 by 1 by infinity, which is equal to 0. So you will get the answer 1 by 9. So it is from n1. So this is the option you get, which is Pastel series. So when n1 is equal to 3 and n2 is equal to infinity, we get this value. So it is, the answer is Pastel series. Okay, so if you see the options here, if you see the options over here, so you can, for trial and error method, you can use these values. Okay, so we get our answer is 3. Our answer is 3. Okay, now coming to 11th question. For hydrogen atom, the orbitals with low energy are. So they have given you a set of options over here, and you need to tell who has lower energy. Now, hope you have taken a screenshot. Just rubbing. So what does the n value suggest? The principal quantum number n. N value, what does it do? What does it tell you about? It tells you about the energy of orbitals, right? Higher the value of N, more is the value of energy. More is the energy of the orbitals, right? Now, here they have given you a set of options. From there, you have to determine which of them is which orbital. For example, the first one, A. So we are doing the 11th one. A is 4s. Okay, so here N is equal to 4. Okay, B is 3px. It is N is equal to 3. Next one is C, 3dx square minus y square, which is where N is equal to 3. Okay. Students, for p orbital, px, py, and pz have the same energy, and then the 5d orbitals are dxy, dyz, dzx, dx square minus y square. These are the orbitals of d, dz square. All of them, they are degenerate, which means they have the same energy. Okay, so that is why they have just shown one of the d orbitals here. Okay, then d is 3dz square. Okay, here also N is equal to 3. Okay, E is 4pz, where N is equal to 4. They have asked you here which has the lowest energy. We know that higher the N value, more is the energy. So that means vice versa, lower the N value, low is the energy. So which of them have comparatively, which of them have lower N values? These three of them. So B, C, D is our answer. So B, C, D is our answer. They have lower energy compared to A and E. Okay. So this is how we do. Okay. Now students, hope you have taken the screenshot of the next question. Okay, just coming to the 12th one. The wavelength of an electron of kinetic energy. So kinetic energy is given to you, which is 4.50 times 10 raised to minus 29 joules. Okay. Kinetic energy is given. You have to find the value of lambda. This is your question. And to the nearest integer, something times 10 raised to minus 5 meter. This is what you have to find. And they have given you the mass of the electron. Okay, so you have to use the mass of the electron. Now, students, you already know the value of wavelength is h by root of, this is the relation between lambda and kinetic energy. Okay, we have done the derivation in one of the videos, yes. So we substitute the value lambda is equal to, the value of Planck's constant is given 6.6 times 10 raised to minus 34 joule second by root of 2 times the value of mass is given 9 times 10 raised to minus 31 kg. And the value of kinetic energy is also given to you, 4.50 times 10 raised to minus 29 joules. Okay. Now, when you do the calculation, it comes to 6.6 by 9 times 10 raised to minus 4. Okay.
Okay, and for calculation purpose, 66 by 9 times 10 raised to 5, which comes to be 7.33 times 10 raised to minus 5, because they have asked in terms of nearest integer something times 10 raised to minus 5 meters. Okay, so this is how you. Okay, students, I show the next set of questions. You can take a screenshot of the questions. Okay. So we have done with the 12th question as well. Now coming to the next set of questions. Okay, please take a screenshot of this. Now students, coming to the 13th one, the electron in the nth orbital of lithium 2 plus ion is excited to n plus 1 orbit using radiation energy. Okay, and the value of n, and they have given the energy of the hydrogen atom. Okay, now sharing the screen. Okay, we are doing the 13th one now. So the electron is excited from n to n plus 1. Okay, this is the, and energy is of the radiation is, energy of the radiation used, minus 17 joules. Okay, you have to find the value of n. Okay, and for the energy of the hydrogen atom, they have given the value 2.18 times 10 raised to minus 18 joules. It's in joules, not in EV. Okay, so it's in joules to make our calculations easier, because the energy radiation that's given is also in joules. Okay, now we use the energy formula. 2.18 times 10 raised to minus 18 by 1 by n1 square minus 1 by n2 square joules. The value of energy, the radiation is given to you, minus 1.47. So we use 1.47 times 10 raised to minus 17 joules. Okay, so 1.47 times 10 raised to minus 17 by 2.18 times 10 raised to minus 18. The joule and joule gets cancelled. 1 by n1 square minus, I'll take a square bracket, minus 1 by n plus 1 square. So here it is n plus 1 the whole square. So if this gets cancelled and we are left with minus 1, right? Minus 1. And here I forgot to write the value of Z. Z is our lithium ion, Z is 3. So here we have times Z square. So that is 3 square. So I get here 9. Okay. So so this is our formula. So our formula is energy is equal to RH times Z square 1 by N1 square minus 1 by N2 square. Okay. So because it was a lithium, we had to use this Z, which is equal to 3. Okay. So this comes to our calculation comes to 1.47 by 1.962 is equal to 1 by N square minus 1 by N plus 1 the whole square. Okay. Now, here, if we calculate this value, this comes to roughly 0.75. Okay. This value comes to 1.47 by 1.962, roughly comes to 0.75. Okay. N square minus 1 by N plus 1 the whole square. Now 0.75 we can write it as 3 by 4 for our calculation, to make the calculation easy. N square minus 1 by N plus 1 the whole square. Now we use the trial and error method again. Okay, so we use the trial and error method again, and in case suppose we have N is equal to 1. Okay, let's check out what it is giving. We are just doing trial and error method. So 1 by 1 square minus 1 by 1 plus 1 the whole square. So this comes to 1 minus 1 by 2 square, that's equal to 4. So what do we get? 3 by 4. So our N value is what? N value is, so our N value is 1. Okay, so students, we just solved it, and by trial and error method, we found the value of N to be 1. Okay. I hope you have taken the screenshot of the questions, students. Coming to the 14th question. Coming to the 14th question. Okay, there is a diagram shown and a graph shown rather, X-rays spectra of elements showed regularity when frequency to the power n, that is nu raised to n of X-rays emitted, is plotted against atomic number Z. The following graph is obtained. So you can see a graph like this where nu raised to n, okay, the frequency nu raised to n is plotted against Z, the atomic number, right, is obtained. So the value of n you have to find out. You have to find out the value of n. Okay, so you get a value like this. Okay, now we know the energy is given by h nu, when nu is the frequency. Okay, and energy for hydrogen 13, or the energy of the nth orbital 13.6 Z square by N square electron volts. Okay. Now, if I'm substituting or if I'm equating the two energies, H nu is equal to 13.6 Z square by N square. Okay. We can see that nu is directly proportional to Z square. Right? So, if here we can say nu of half, that is square root of nu, is directly proportional to Z. Right? So that means if I say V raised to N is directly proportional to Z, so the value of N is half. If nu is directly proportional to Z, then we will get a straight line graph. So the value of N is half. So the value of N is half. So this was our 14th question. Okay. The 15th one is the number of s electrons present in an ion, okay, with 55 protons in its unipositive state. So we have 55 protons. That means number of electrons is also number of s electrons present in an ion with 55 protons in a unipositive state. Okay, so the number of protons is 55. Now, here unipositive means one electron has been removed. So the electron will be, number of electrons will be, should have been 56. Then one electron is removed, then it became 55. So first we will write the configuration of this particular atom. Okay, so we have 1s2 following Aufbau principle, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 5s2, 4d10, 5p6, 6s1. Okay, now this is for when the number of electrons or atomic number is, or number of electrons is 55. Okay, now number of electrons is 56. But in this case, they have already told that one electron, it's a unipositive, one electron is removed. So the electron is removed from the s orbital. So this one is removed. Now we have to check how many electrons are there in the s orbital. So we just, first I'll just underline the electrons in the s orbital. Okay, so 2 plus 2 plus 2 plus 2 plus 2, which is equal to 10 electrons. We didn't take this one, 6s1 electron, because they have said that one electron is removed. I mean, it's a unipositive ion. Okay, so that's why. So the answer is 10 students. So this is our 15th one. So what I did, the unipositive means one electron is removed. So I just took the number of electron 56. So from 56, one electron is removed. So I just wrote the configuration and then calculated it. Okay. Now coming to the 16th one, you can write the configuration 55 directly and do it also. Just I wanted to write down the configuration and do it so that you understand the configuration well. So question number 16. Okay, the shortest wavelength of hydrogen atom in alignment series is lambda. So the shortest wavelength is lambda, and the longest wavelength in the Balmer series of helium. So they have asked you the longest wavelength in the Balmer series of helium ion. Okay, so you can see these are all hydrogen-like species. Okay, He plus ion. This is, or they are all behaving as hydrogen-like species. Okay, so we use this formula 1 by lambda equal to RH Z square, energy of hydrogen, 1 by N1 square minus 1 by N2 square. Okay, and this is the shortest. Okay, please remember students, shortest wavelength means longest transition. Infinity to 1, all these are longest transition will give the shortest wavelength and vice versa. Okay, now if I use this for, I'm using this formula. Okay, so 1 by lambda, this is for hydrogen, is equal to where Z is equal to 1. RH, so 1 square. So shortest wavelength means shortest wavelength. Shortest wavelength means longest transition. So maybe from infinity to 1. So 1 by N1 square is 1 square minus 1 by infinity square. Okay, I'll keep this as equation 1. Okay, now for helium ion, Z is equal to 2. Okay, now for helium they are saying longest wavelength. If it is longest wavelength, then what will be the transition? Transition will be shortest. Maybe for from 3 to 2, because it is Balmer series. If it is Balmer series, then N1 is equal to 2. Balmer series. From any higher orbitals to N1 should be 2. Okay, so let's substitute it. This is for helium ion. Okay, is equal to RH times Z square 1 by 2 square minus 1 by 3 square, which is equal to 4 RH one by lambda for helium ion. Okay. This I'm taking it as equation 2. So, if I divide equation 1 by equation 2, equation 1 divided by equation 2, we have, this is for hydrogen. So 1 by lambda H is equal to RH by 1 by lambda helium ion for RH 5 by 36. Okay, so I cancel these common terms. I get lambda He ion by lambda HEH 36 by sorry, I have made a mistake by writing 7. This is 4, as you can see. This is 4. By mistake, I wrote 7. This is 4, right? So 4 times 5. Okay, so when I solve this, I get it as 9 by 5. Or rather, we write it as the answer we write like this. Lambda helium ion is equal to 9 by 5 lambda hydrogen. Okay, so this is how you solve. Okay, so this is your second option. Second option. So students, hope you understood how to do this. Coming to the next set of questions, I'll just show the questions so that you may take a screenshot. Okay, I'll just show the questions. We finished until the 16th question. Okay, this is the next set of questions, students. Please take a screenshot of the questions. Now, students, if you see the 17th one, maximum number of electrons that can be accommodated in the shell with n is equal to 5. Okay, I hope you have taken a screenshot. Now, okay. Now, students, they have asked maximum number of electrons that can be accommodated in the shell with n is equal to 4. This is our 17th question. Okay. Now, n is equal to 4. Now, here we have, for n is equal to 4, we have 4s shell. So, maximum number of electron that can be accommodated in this. Okay. We have n, when n is equal to 4, we have 4s, 4p, 4d, and 4n, 4f. So, just the maximum number of electrons. That's what they have asked. It's a straightforward question. So, s orbital, you know, it can accommodate 2 electrons. In 4p, it is 6 electrons. In 4d, it is 10, and it is 14 in case of 4f. So the total comes to 32. So the answer will be 32 electrons. So your option will be the second option comes to 32. Okay. So this is just, so it was a straightforward question. You just had to tell the number of electrons that can be accommodated in that. And n is equal to 2, n is equal to 4 shells. Okay. Now coming to 18th one. In an atom, how many of the following metal ions have similar values of spin-only magnetic moment in gaseous state? Okay, so this particular question, they have given you the atomic numbers of different transition elements. You will be learning later that these are transition element. Okay, vanadium. Okay, vanadium, the atomic number is 23. Okay, vanadium is 23. Now students, when it is 23, I just write down the configuration. Okay, 1s2, 2s2, 2p6, 3s2, 3p6. This comes to 18 electron, right? Now, this is we have not finished writing the configuration, and after this, after 3p6, we have 18 plus 2, 20, and then we have 3d, 1. Or rather, okay, students, this is our configuration. Okay. Now, students, there is in most of the books, in all the books, they denote this numbers constitute 18 electrons, and this is 18 means it is the atomic number of argon. So whichever if it is denoting the atomic number of argon, we write the vanadium configuration like this: argon, that means 18 electrons. Okay, then the rest of it we write 4s2. So this is just a method of denoting it so that we can save some space. Rather than writing the whole thing, we write it in this way. Okay, so why I'm showing it like this, because we will be using this kind of a configuration. We will write like this. Okay, now this is for vanadium. What they have asked is not vanadium. They have asked for vanadium 3 plus ion. Okay, so for vanadium 3 plus ion, usually the electron is lost first from the s orbital and then from the d orbital. So it has to lose how many electrons? It has to lose 3 electrons, because then only vanadium will get 3 plus positive ion. So 3 plus positive ion of vanadium has a configuration like this: 4s0, 3d, 1, because it has lost the 2 electrons from s orbital and 1 electron from d orbital. After removing from s, then only it can remove from d. Okay, so this is the configuration of vanadium ion. For S0, 3D, 1. Okay, students, I'm just referring to the configuration also over here so that it's easy for you. Similarly, for chromium. So chromium, I'll just rub this off and show for chromium. Chromium, the atomic number mentioned is, if you're thorough with the configuration, you can just quickly write it. Chromium, it is 24. So similarly, argon 18. What all are left? 4s2, 3d 4. 18 plus 2, 20, 24. But they have not told chromium atom. They have told chromium ion, 3 plus ion. So that means how many electrons are lost? How many electrons are lost? 3 electrons are lost. First, from where the electrons will get lost? From where the electrons will move out first? First, the electrons will move out from 4s. So 4s0, 3d. Okay, so this is argon 18, 4s0, 3d, 3. Students, I made a mistake here. This is, although I said 3d2, I wrote it as 1. Okay, so this is for vanadium and this is for chromium. Okay, similarly, iron, I'll just show one more. Okay, because from vanadium, because here 3 electrons are lost. 2 from here and 1 from here. So that means 3d2, right? So that's what. Coming to iron. Iron, the atomic number Fe is 26. So that means argon 18. Okay. Argon 18. Then we have 20, 26. So the capacity of D is until 10. So we get this configuration, right? Now, iron is, we are getting as iron 2 plus in the question, right? So iron 2 plus means how many electrons it will lose? It will lose 2 electrons. So directly it will lose from where? 4s0, 3d, 6. So we have argon 18, 4s0, 3d, 6. Okay, so we got iron also. Now we are left with one more, which is nickel. Nickel, the atomic number is 28. Nickel, the atomic number is 28. So we write down the configuration as 4s2, 3d, 8. 18 plus 2, 20, 28. Now, nickel is 3 plus, so that means 3 electrons are lost. So that means it will lose from S, 2 electrons from S, and 1 electron from 3d. So we get what? So nickel 3 plus, argon 18, 4s0, 3d 7. This is 0, not 6. Okay. So students, so these are the 4 configurations. Okay. Now from here, what they have asked is, Which of them have similar value of spin-only magnetic moment in gaseous state? You have to check the number of unpaired electrons. Okay, now here the number of unpaired electrons is 2. So the number of unpaired electron is 2. Here the number of unpaired electron is 3. Okay. Here the number of unpaired electron, 1, 2, 3, 4, 5, 6. The number of unpaired electron is 4. Okay. Here the number of unpaired electron, 1, 2, 3, 4, 5, 6, 7. The number of unpaired electron is 3. Now, here if you see, chromium and nickel have similar value. Chromium ion and nickel ion have similar value of unpaired electron, and that is why they will have the same value of spin. Okay, so they will have similar value of the spin-only magnetic moment because they have the similar number of unpaired electrons. So students, we just wrote down the configuration and checked the number of unpaired electrons. Okay, so this was our 18th question. Coming to the 19th one. In an atom, the total number of electrons having quantum number n is equal to 4 ml1, that is azimuthal quantum number 1, and spin quantum number minus half. Okay, now here you have n is equal to 4 and L values 0, 1, 2, 3. Then n value is 4. L value will range from L1. So when n value is 4, L value will range from L2 So when n value is 4, we have L value 0, 1, 2, 3. Okay. Now, when n value is 0, we have ML is 0. When L value is 1, we have the magnetic quantum number. When L value is 0, the magnetic quantum number is 0. When L value is 1, we have write it as caps 2, 3, right? When L value is 1, we have -1, 0, +1. When it is 2, -2, -1, 0, +1, +2. When it is 3, we have -3, -2, -1, 0, 1, 2, 3. Now here we have, the question is, in an atom, the total number of electrons having L value 1 and spin quantum number, that is the magnetic quantum number is 1 and the spin quantum number is minus half. You know, whenever there is an orbital, one electron will have +1 plus half per spin, and one will have minus half spin. So each one will be having plus half, other one will be minus half. So here we need to check the ML values as 1. Okay, so we'll not look at the sign for this magnetic quantum number. So we have 1, 2. Here we have 2 of them. Here we have 2 of them. Here also we have 2 of them. So in each of them, one will have plus half minus half, plus half minus half. So we have 2 plus 2 plus 2. That is 6 electrons. Okay, so each of these subshells, okay, will have 1 electron each having minus 5 spin. So this will have 1 minus half spin. This will have minus 1 minus half. So like this 1, 2, 3, 4, 5, and 6. Okay, hope this is clear. Coming to the 20th one, we have the wavelength of a radiation having this is the wavelength having wavelength for a radiation having 5,500 Armstrong wavelength is x times 10 raised to per centimeter, 10 x times 10 raised to 10 per centimeter, the value of x. So you have to find the value of x. So the wave number, the question is the wave number for a radiation. So this is the wave number. Wave number is given by 1 by lambda, where 1 by lambda is nothing but wave number. Okay, so mu bar, which is wave number. So you need to find the value of x. Okay, now here I just have to substitute. They have asked in centimeters. So Armstrong to centimeter, Armstrong to centimeter multiplied by 10 raised to minus 8. Okay, so times 10 raised to minus 8 equal to x times so you get the answer as 17241. This is your answer. Now coming to 21st one. I'll just take a please take a screenshot of the next set of questions. Okay. Till 20th we have done. So this is our next set of questions. First one. Okay. If you see the 21st question, consider the following. The pair of electrons present in degenerate orbitals. Degenerate means those orbitals having the same energy, like our 3p orbitals or the 5d orbitals. All these are degenerate. Okay, I hope you have taken the screenshot. Okay, now coming to 21st one. 21st one. Now here, degenerate means same energy as our three p orbitals and all the 5d orbitals. Now the first one is L is equal to 1. So here we have 0 when the L has values 0, 1, 2, 3. This is S, P, D and F. L is equal to 1 and N is equal to 3. So we have, we can find out this by N plus L rule. Higher the value, higher will be the energy. Same value, same energy. So this comes to 4. Okay. B, the L value is this is the first one. Okay. So this is the, in A, there are two options, A and B. In B, N is equal to 3 and L is equal to 2. So N plus L value will be, N plus L value will be 5. Okay, so one has 4, the one has 5. Okay, in B, the first one is, B also has 2 of them. N is equal to 3, L is equal to 2. So N plus L value will be 5. Then there is another one where N is equal to 3, L is equal to 2. So 3 plus 2 gives 5. So one of them we got as same energy, same value. Okay, so we got our answer, but we need to check for the others also if there are, because they have given like as a multiple option this thing also, multiple option also. So C is N is equal to 4, L is equal to 2. So 4 plus 2 makes 6. B is N is equal to 3, L is equal to 2. So 3 plus 2, 5. So this is not our option, this is not our answer. What is our answer? B. Only B. B is our answer. Okay, so this is just the application of N plus L rule. To find degenerate, I have already written the meaning. Those have the same energy, and those having the same N plus L value, those orbitals will have the same energy. Those with higher values will have higher energy, vice versa. Now coming to 22nd question. The energy of 1 mole of photons of radiation of wavelength. So wavelength is given 300 nanometer. And energy of 1 mole of photon is given by h nu or hc by lambda times the value of 1 mole, that means Avogadro number of atoms, where Na is the Avogadro number of atom. Avogadro number of atom. Okay, so we have H value you know, and it is given in the question also, 6.63. Take the same value that's written in the question, 10 raised to minus 34 joules second. Times the value of C is speed of light. It's also mentioned in the question, 3 times 10 raised to 8 by 300 nanometer. So we need to make it into meters. So 300 nanometer to meter. So 300 times 10 raised to minus 9. So times 10 raised to minus 9. We also have to substitute the value of Na, which is also given in the question, 6.02 times 10 raised to 23 per mole. Okay, so when you solve it, you come to 399.13 10 raised to 3 joule per mole. Here, the options is in kilojoules. So 399 kilojoules per mole. This is our answer. So please remember this formula is just another version of h nu, which is equal to hc by lambda. And we multiplied with Na because they have asked for 1 mole. Now coming to the 23rd question. The pair in which ions are isoelectronic with aluminium ion. Okay, so 23rd, aluminium ions. Isoelectronic means same number of electrons. Okay, so aluminium 3 plus. Okay, aluminium has actually aluminium has, the atomic number is 13. So the number of electrons is 13. Okay, but if it is aluminium 3 plus, the number of electrons will be 10. So it's a 10 electron. So we need to check which of them has 10 electrons. Okay, so students, please remember that oxygen, magnesium, oxygen ion, magnesium 2 plus ion, they all have 10 electrons because oxygen, it is the atomic number is 8. That means oxygen atom has an atomic number of 8. That means 8 electrons, right? But when it is oxygen 2 minus, that means it is gaining 2 electrons. So it is gaining 2 electrons. When it gains 2 electrons, how many electrons it will get? It will have 10 electrons. Similarly, magnesium atom has 12 electrons. But when it is forming magnesium ion, it will gain 2 electrons. Sorry, it will lose 2 electrons. Lose 2 electrons. This is gain. When it loses 2 electrons, you will get 10 electrons. Right? So our answer is magnesium and oxygen. So our answer is magnesium and oxygen. That is our D option. Okay. Now coming to 24th one. 24th one, the minimum energy that must be possessed by photons in order to produce photoelectric effect with platinum metal. Okay, so threshold frequency is given. Okay, so threshold frequency is given, which is 1.3 times 10 raised to 15 per second. Okay, so you have to find the minimum energy. So the minimum energy we know is the work function and is given by h nu. So 6.6 times 10 raised to minus 34 times 1.3 times 10 raised to 15. Okay, so this is joule second. This is per joule. So we get 8.58 times 10 raised to minus 19 joules. Okay, so this is your answer. So students, we have one more question to go. Just take a screenshot. Okay, just share the screen. For the 25th one. Okay, this is regarding the Heisenberg's uncertainty principle. Okay, so we have so this is about the Heisenberg's uncertainty principle. So they have mentioned the uncertainty in velocity and position they have given. Okay, so uncertainty in velocity is delta V 2.4 times 10 raised to minus 26 meter per second. And position is 10 raised to minus 7 meters. So you have to find the mass of the particle in grams. So we know this formula, delta X times delta P is greater than equal to H by mv. So we'll just write equal now. Sorry, H by 4 pi. Now P is given by mv, right? So delta X times delta V times m is equal to H by 4 pi. This is our unknown thing we need to find out. We substitute the values. M is equal to H by 4 pi delta X delta V. We know the value of X and V. Okay. So the value of H that's given is 6.626 times 10 raised to minus 34 joule second by 4 pi times 10 raised to minus 7 times 2.4 times 10 raised to minus 26 meter per second. This is meter. Okay, so we have 6.626. We will cancel the values of this this gets cancelled. We are left with 10 raised to minus 1. Okay. times 10 raised to minus 1 by 9.6 times pi. The value of pi is 3.14. Okay. So when we solve it, we get it as 0.0219 kg. Or if we want to make it into grams, 21.9 grams. Okay. Or if we want to make it into the nearest integer, we make it into 22 grams. Okay. So students, we solved some of the past paper NEET questions. Okay. So that's all for today. Thank you, students. Have a great day.